on this computer. Okay, so the midterm, my plan right now is to pass it out Wednesday, unless Kaiser is also giving his midterm next Wednesday, in which case we'll adapt. But I'll be passing it out on Wednesday. You'll have all day Thursday to work on it. It's due at start of class on Friday morning, and you're gonna have to you'll have to scan it and upload it into Canvas like you do with your worksheets and the homework, which is up on Canvas right now as well. I made it up last night. Let's see, let's show you where that is, and let's share screen with you. Share Canvas. Okay, yep, green box around it. So hopefully you're looking at the Canvas screen, and there's homework 7, 3 problems. I think I promised you that. Very similar to what we've been doing on the worksheets, very similar to the most recent worksheet and the things we've been doing in the last couple classes. Probably comprise most of the homework. Here are all the tutorials. By the way, the stuff we're doing next, we started last class, the chapter 4 stuff. The first tutorial is spherical harmonics. You'll notice that's due Friday. The last tutorial, Dirac notation, that's due today. Okay, so that's what you're looking at. And then hydrogen 1 will be due next week. Won't be on the exam. Okay, the scope of the exam will be scattering, because if you remember, we did not have scattering. We were up to the finite square well on midterm 1, so it'll be scattering the last part of chapter 2. So I guess that's these 2 tutorials. There was the scattering for the delta well and scattering for the finite well, and then chapter 3, the formalism. So that'll be the scope of the exam. And I'm looking at like 3 problems, much like homework 7, except adding some stuff from scattering on it. And then of course the tutorials you've been working on in chapter 3 and the 2 tutorials from chapter 2. So that's the scope of the exam. Take home, open book, open notes. You can use internet resources. You have the ability, of course, to use any calculation tool, Wolfram Alpha. Those of you that have like a TI Inspired, good to go. Any calculator you want. The one exception of resources is another human being, and that's both an online human being. Look, my dog's here. He just came to check on me. Online resources, like if there's a tutorial, chat room kind of thing, online tutors, those are off. Any questions you send to Kaiser's so that he doesn't realize it's an exam question, or any of the other faculty, no good. You can't talk to each other, but that'll be the exam next week. Okay, any questions on that? All right, then let's get back onto the material we were talking about. I'll stop sharing Canvas with you and start sharing instead the PowerPoint, which, yeah, I guess I want that one. I've got 2 open right now. And remember where we were last time, because this is the problem with upper level physics courses. I think you can't get through a full problem in a 50-minute period of time. That's just the way the problems work. They're more complicated than that. The days of a problem that takes 5-10 minutes to solve are long gone. And just go way back, I guess, to what we were talking about. Nope, I guess I got to actually click on it. I want to go backwards there. There we go. Now I can move. We were starting with the time-independent Schrodinger wave equation. Except we were doing it in 3 dimensions. So in place of the second derivative with respect to x, we put in a Laplacian, and that was what we talked about. We went through this process of solving a partial differential equation of this type called separation of variables, and went through the separation process last class. The 2 separation pieces that we've been using up until this point, separated back one. Separated into a radial piece, which we'll be spending more time with today and Friday, and an angular piece, and the name of those functions are r and y. Y's are called spherical harmonics, and that function is a function of theta and phi. Okay, so we worked through that to strip off the radial equation, which is sitting right here, and we'll be talking more about that in a bit. Pen, yeah, red's good. Okay, so that's the radial equation. Oops, come on back. You're supposed to be there. Pen, there we go. That's the radial equation we'll be talking about here in a bit. The angular equation was this guy, and you notice it still has derivatives with respect to theta and derivatives with respect to phi. And of course, there's a theta mixed in that term. And so the next step was to separate out the angular piece. So we took this spherical harmonic function y and we split it up into a theta and a phi piece. And we worked through that and did a separation of variables step again. The separation constant for the phi piece we called m. The separation m squared actually, which gave us a number m, and the separation constant between the radial and the angular piece y was this l, but it wasn't l squared. It was almost l squared. It's l times l plus 1, which has an L squared term in it, similar piece, but it just makes the way that you index the solution a whole lot easier. Let's just remind ourselves what the angular piece in the phi direction is, and it's that guy right there. That's the phi piece. You set that equal to minus m squared, and that becomes your differential equation. And I proposed that's the solution. I showed, well, yeah, if I take the second derivative with respect to phi, put it in right there, put phi in right there, it does work. You'll notice it's not a good differential equation solution because I've only got one term, and you recognize if e to the im phi is a solution, so is e to the minus im phi a solution to this differential equation. So we're missing that, but we're going to allow m to be a negative number, and that solves that dilemma. There's also no constant that would be in front of both the e to the im theta term and its companion e to the minus im phi. Those would be constants that would be in place. We're okay with that. We're going to put that with the other part of our separation of the spherical harmonics. We'll just lump that with the theta piece, okay? And I guess the other thing we realize out of this is in spherical coordinates, and there's my right-handed system right here, x, y, and z. Okay, remember that for a particular direction, vector r right there, I guess, that's what we're calling theta. And then its projection, getting pretty good at drawing with this mouse here, its projection into the xy plane, that's phi. And so I guess if I'm right here at some angular position phi, if you went all the way around phi plus 2 pi, you'd be at the very same angular position. So if you had r and theta the same, and you came back to that position by circling around another 2 pi, another 360 degrees, you'd be at the same point. The function has to have the same value there. And if you look at that, if e to the I m phi and same thing, but adding 2 pi have the same value, well, I just split that out algebraically into two pieces. The only way this can be equal to that is if the thing I'm circling right now is equal to 1, right? If the thing I'm circling right there is equal to 1, and the important point is that then m must be an integer. It could be a positive integer, it could be a negative integer, but it's an integer. And so that's one of the things. And the phi piece of the wave function that we're solving for, the eigenfunction, now we can say with confidence that we understand it's a function, not a matrix this time, because that's what works for the hydrogen atom. But there'll be parts of the hydrogen atom we'll treat as matrices. If you're wondering when we're going to link back into chapter 3, but that is the phi function. Okay, so that leaves the theta part, and we went through this last time, and it was somewhere around here where we finished up, and we said, well, if you go back right here and you look at this other part right here and set it equal to that separation constant m squared, okay, well, you do that, you rearrange the thing, you get an equation that Legendre studied in great detail in the 1800s. He worked out all the math. We're not doing this one. We are going to do the radial math. In fact, that's what the next worksheet, the tutorial, that's actually Friday's tutorial, will take you through. We'll start some of it. I'll get you going and we'll finish it up on Friday. But that solution is well solved. Okay, that differential equation is well solved. And this is the solution. There's the constant that I promised you. I made it A, it could have been C, whatever. And the answer to this differential equation is this series of mathematical functions called associated Legendre polynomials. You notice they have two indices. One of the indices is this L, which was the separation constant between the radial and the angular spherical harmonics, y, the r and the y function. Okay, remember that separation constant was L times L plus 1, and I said the index would work out then. And the other was M. It's the same M that's in the phi piece of the angular solution y, because remember y is equal to a theta piece and a phi piece. And of course, I'm saying them and writing them in the exact opposite order. Okay, so M is definitely associated with that guy. We learned a lot about M. M had to be an integer. It could be a positive or negative number. Now we're looking at this piece, and the solution to that theta, interestingly enough, depends on that same M right there because it's in the differential equation. Okay, so that's an interesting thing. All right, so I think I was starting to take derivatives last time. Oh yeah, and this associated Legendre function has in it something called the Legendre polynomial, which a guy named Rodriguez worked out all the possible values of. And so actually all of this is tacked on to the end right there of these associated Legendre functions. Okay, and you can see I'm taking a derivative with respect to L. That's like a first derivative, a second derivative, a third derivative for the Legendre polynomials. They only have one index. They're only indexed to the separation constant between R and Y, the spherical harmonic function. Okay, whereas the associated Legendre polynomials have two indices, M and L. Okay, and you can see where the M shows up right here and right here and right here, whereas the Legendre polynomial, that's where the L's hidden, so it's hidden in that piece right there, right there, right there, right there. You can see where the indices matter right there in the solution. So whatever the value of L is, this is actually an infinite number of differential equations that were being solved, and the answers are depending on what you have for a particular L and what you have for a particular M. The rest are just mathematical sines and cosines. Okay, so working with these things, and this is about where I think we left off last time. According to Rodriguez formula, which is this thing, that's what's known as Rodriguez formula. I guess if you're looking for the 0, 1, where L is equal to 0, you're taking a 0th derivative. That's defined just to be a constant. You got this thing to the 0 power. That's just a 1. That's all 1, 1, 1. First guy was 1. The second guy, and I'm going to erase some of that because I've highlighted stuff and now it's hard to read, I think. And we're just going to do the Legendre polynomials first. We'll play with those, and then we'll talk about the associated Legendre functions. Okay, so I'll get my pen back. And so now the next one, the 1, P1 function, I put in a 1 right here, and so that's x squared minus 1. I'm taking the first derivative of that, and I've got 2 to the first power and 1 factorial. Let's see, 2 to the first power is just 2, 1 factorial is 1. I'm taking the first derivative of that. The derivative of x squared is 2x. The derivative of 1 is 0. I got 1 half times 2. Hey, look, it's just x. Okay, that's the first Legendre polynomial. The next one up, well, L is now 2, so I'm taking a second derivative, right? I'm taking a second derivative, and this thing right here is squared. It's 2 to the 2 power, that's 4. 2 factorial is still 2. Okay, so that's what I have to do. I worked that thing out, and I got 1 half 3x squared minus 1. Okay, and just one thing about these Legendre polynomials, I don't think I asked last time. If you've taken the advanced E&M class, and this is what I'm wondering, who's done that already, you should be very familiar with these, because when you solved what's called Laplace's equation, it's a method of determining what a potential is for some charge distribution, like you would have done in 112 class by, say, integrating over the charge distribution, or maybe integrating an electric field to get a potential field. Okay, those are methods. The other way is to solve Laplace's differential equations. All you need to know is the boundary conditions, and you can also solve for V. And if you've taken that class, you recognize this equation right here has Legendre polynomials as its solution in spherical coordinates or in Cartesian coordinates. Okay, now a couple things about this right now before we move out of the Legendre polynomials and talk about the associated Legendre functions. You can see there's no such thing as a half a derivative. There's, we've got first derivatives, second derivatives. We don't have 3/2 derivatives or 5/2 derivatives, 1/2 derivatives. They don't exist. Okay, so that tells us something about these values of L and M. We already know a little bit about M. Now we know a little bit more about L. L must be a positive integer. Okay, must be a positive integer, and that's kind of the deal. Yeah, I think we want to talk about how big L and M can be here in a second, and we'll talk about that on the next slide when we stop talking about Legendre polynomials. Okay, and I think I showed you this last time. They're tabulated. I just did the first 3 right here. You can go through exactly the same process to get 3, 4, 5, 6. They're graphed. In your textbook, he only graphs the first 3, but you can see P0 is just a constant 1. P2 is a parabola. P3 is a cubic. Let's see, 4 here is going to be 0, 1. What did I skip? I also skipped 1, didn't I? There's P1. I may have been pointing to the wrong piece right there. P0 is a constant. P1 is just a linear function, right? X. P2 is the parabola. P3 is the cubic. P4 is this pink line right here. So it goes boom, 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 boom. So that's P4. You can see P5. You get the idea. They're just polynomials. However, I do want to point out that the Legendre polynomial, which was a piece of what we're about to talk about more, the associated Legendre function, is of the cosine of theta, not x. So you're really substituting in where the x's are, the cosine of theta. Okay, and so that's the thing to keep in mind. All right, moving on to these associated Legendre polynomials then, and I think I talked about this a little bit on Monday. So now the things we've just solved for, and I showed you the chart, those are right there. Okay, those are the Legendre polynomials. The Legendre functions are defined this way. And remember, the Legendre function of cosine of theta is the solution to our differential equation, but we're just going to talk about x right now. We'll make the substitution for cosine of theta later. If you do this and you go, okay, so 0, 0, a 0th derivative, we're saying it's just defined to be 1. P0 is also 1. This guy right here, 1 minus x squared to the 0 power, because m is 0, is 1, 1, everything's 1. Piece of cake on that one. All right. P1 is the next guy coming up. Okay, so I make L equals 1, and then I go to m equals 0. Again, the 0th derivative, so that's just 1. M is equal to 0, that's 1/2, isn't it? Now, what am I doing here? M is 0, 1/2. Oh, I'm sorry, I'm wrong here. This is P1, and it's 0th derivative, right? So P1 is x, taking the 0th derivative of it, okay, which is 1. And then I've got that to the 0 power. All right, I'm confusing myself here. How come I'm coming out with x? P1. That's x. Make sure I got the right chart. L is, we're certainly taking that, plugging that right in there, okay? And then that's 0 because I'm doing this guy right here. I've got that is 0, and I got that is 0. And so 1 times 1 times 1, I guess it's just times x, okay? And so that's what that means. I just bring the x over. Yep. All right, we'll accept that. I did copy it right. Okay, so now I got to do L equals 1 and let M go to be equal to 1. Okay, so let's see. I still have x coming right in there. I've got 1 here now, so I'm taking the first derivative with respect to x of x. So now all of that does go to x, okay? And I've got this to the 1/2 power now, and I got that to the first power. -1 to an odd power gets me a negative sign. Okay, I have 1 minus x squared to the 1/2 power, square root of 1 minus x squared. The derivative of x with respect to x is just 1, and so that's what I'm left with for P11. Okay, here's the important part though, I guess. If I try to take m equal to 2 now, holding L equal to 1, well, I'll do the same thing, but now this will be a second derivative of x with respect to x squared. And of course, it goes to 1, then the derivative of 1 is 0. This is 0. The same would be true if I had m equals 3. The same would be true if I had m equals 4. Any value of m greater than, notice, L is going to yield a 0 when I try to take that derivative. So that tells me something about my relationship between L and M. M must be less than L. Okay, if I try to take m equals 3 and m equals 2 when L is equal to 1, doesn't work. Okay, L must be a positive integer because, again, derivatives of the Legendre polynomials have to be first, second, third. And now right away we can see that m has to also be an integer because we said that when we talked about the multi-valued phi function. Okay, and it has to be less than L. All right, so we keep, just to prove it, I didn't look at this last time. I think I cut off right about here. When I go cycle up to the next value of L, 2, and I start at 0, okay, that's great. So now I've got P2 I'm working with. So I'm working with this thing instead of X now. And that's what I'm plugging right in there instead of that now. Okay. And I'm taking the 0th derivative. That just gets me that thing. Okay. And let's see, I've got, this is 0, that's 0. All I got is, it's the same as the first Legendre polynomial. The second Legendre polynomial, the associated Legendre function 2, 0 is exactly the same thing. All right, now we move on to L equals 2, M equals 1. And now I put in my P2. I take the first derivative of it because M is now equal to 1. And this is why they're called Legendre, associated Legendre functions, not polynomials, is because as soon as m is equal to 1 there, I got a square root. This term isn't technically a polynomial. It's a function. And so that's why associated Legendre things are called functions, not polynomials. But it still has a 1 minus x squared, but I'm taking a square root here. Anyway, I do this operation here. I take that derivative with respect to x. It brings down a 2. I can, I guess, factor out the 3x after I multiply through. So let's see. I have the derivative of that with respect to x, so that's 6x divided by 2, 3x, and 0, so 3x with the minus sign, and then the square root here. Okay, works. Try to do the second derivative now, the m equals 2 case. So m is equal to 2 everywhere in this definition up top here. Okay, so I put the function in again, the function being P2 again. Okay, I have to take now the second derivative because m in this case is equal to 2. And let's see, I have to multiply by 1 minus x squared. 2 over 2, that's just 1. That's why I wrote that. So I had to do 2 derivatives here. I did them real quick in my head. I get 6x, and I take the derivative of that again. It's just 6 divided by 2. That's where the 3 comes from. And then that just came out front there. Okay. And I guess the next point, and somebody's going to have to chirp up here, what would that be? Well, that would be, I would take in a third derivative of this function right here. What would the third derivative of that function be? Shout it out, somebody. Make me know you're alive. Got a pulse?
0.
0, there we go. It was an easy question. I just want to make sure everybody was still hearing me. Thank you. Okay, so anyway, it's 0. So again, m can't be greater than L. It just doesn't exist because it goes to 0 right there. That tells us something about the possible values of m. M can only be minus L plus 1, 1, 0, 1, all the way up to L minus 1. So I think the example I talked about last time is if, let's say, L was 3, then I'd have minus 3, minus 2, minus 1, 0, 1, 2, 3. You notice for L equals 3, there is 1, 2, 3, 4, 5, 6, 7 possible values of m that could exist and meet the rules of working through the associated Legendre functions and the Legendre polynomials. Okay, working through some of that is what is on the next tutorial that I showed you that is due on Friday. It really just has you playing with these functions to gain familiarity with them. And then taking some of them and plugging them back into our separated differential equation for theta and seeing if they actually do solve that differential equation. And I went with the easy case where m is equal to 0. So you'll be working with one of those. I think you'll be working with this guy right here, proving it is a solution. And I'm also asking you to prove on this tutorial that these solutions are normalized, because they are, right? If they aren't normalizable and they aren't normalized as we write them, then they're not valid as wave functions, right? They don't fit into what we've now learned is called a Hilbert space. By the way, I called it L2 space, and I think some of the when I was in graduate school, that's what the mathematicians called it. We've renamed it somewhere along the line, but those guys have to be normalized, and so you'll check that on the worksheet tutorial that's due Friday. Excuse me. All right, just a couple pictures of these things, and again, remember I told you I gave you the associated Legendre polynomials L and M as a function of x. Remember, when it is a solution to the differential equation, Schrodinger's wave equation, angular portion, okay, theta portion of the angular portion, it's a lot of subdividing to divide up the problem, make it doable. These are not functions of x, they're functions of cosine of theta. So wherever there was a x, you have to put in cosine of theta. And I think that made great sense. Let's write them as we did them here, because I did them in a particular order. But remember, P10 is x, P10, that was just x. And of course, this one was the next one down, back, no, right there was the next one down, which was minus 1 minus x squared to the 1/2. So let's take a look at that. That was minus 1 minus x squared to the 1/2 power. And so remember, if this is cosine squared right there, this is equal to minus the square root of 1 minus cosine squared. 1 minus cosine squared, of course, is a trig identity, is sine squared. Take the square root of that, it's sine, and this negative sign comes out front. Okay, and so just graphing them, at least in the in 2 dimensions here, that guy right there is just a circle, isn't it? The first one right here, pi 1, is minus the sine of theta, and so when theta is equal to 0, the sine has 0, and as you come down to actually, I think you go this way, don't you? As you come down to 90 degrees, it becomes 1. And then when you come to 180 degrees, the value at 180 degrees is back to 0. And it does the same thing on the other lobe. On the other hand, cosine of theta, this is P1 here, when you're at theta equal to 0, well, the associated Legendre function is at 1. As you come down to 0, I'm sorry, come down to 90 degrees, the associated Legendre polynomial has a magnitude of 1, because that's what the cosine does at 90 degrees. And then at 180 degrees, it becomes 1 again, and it comes back up. You can do the same thing for the P2s. Okay, you can see here's P21, which is this guy right here. Okay, it's kind of this little leaf sort of looking thing. P20, which is this one right here, that's plotted right here. Okay, and basically it's pretty easy to see these guys, right? It's a little harder to see those without some sort of graphing program like Mathematica or Maxima or something like that. In any event, these things exist. Where's my other? Oh, there. I want to show you what they look like. Okay. Well, hang on that. We'll come back. I want to talk about normalization first, and I'll show you what they actually look like in 3 dimensions then. This is a convention that we have. Remember I said just a second ago, these functions have to be normalizable. All right. And you're going to check that. And we've kind of worked up this, right? Because now we know what both phi is and what theta is. Phi is this e to the I m phi, and these are the associated Legendre functions, a PLM of cosine of theta. Okay, and so that's what we're talking about here. Well, when we normalize in 3 dimensions in spherical coordinates, that's the volume element. And the convention is how we're going to split up that volume element between the radial and the angular piece. Okay, and so if you look, that's clearly radial, that's clearly radial. This and this, that's angular. So when you're checking to make sure that this is equal to 1, which, by the way, would allow you to solve for that coefficient a right there, right, is to make sure it meets this. We're going to subdivide and put the pieces associated with r in the integral associated with r, because this is really a triple integral, right? This is an integral over r, it's an integral over theta, and it's an integral over phi. Okay, so the piece that's r, we're going to bring that part and that part of the volume element, okay? And this guy right here, when we do y, which is this is a double integral now over theta and over phi, well, we're going to have that piece in there, okay? And so if we figured out, hey, here's my y right here, and I put in phi and theta, when I normalize it, I don't worry about r. R is going to be, when we figure out what the r function is, we just normalize it over this range right here. By the way, the symbol I picked right here is capital omega, and that's a solid angle. Think about that as a cone, right? If I have something like that, okay, a solid angle is defined right there, and that's the symbol we use for it. So this is a differential, a very small solid angle. Solid angles are defined in the way you might expect. If theta, a two-dimensional angle, is an arc length over a radius, right? And let's put the radius of my cone right here. A solid angle is defined as this area divided by the radius. So that's a two-dimensional angle, I guess, and it's defined in a logical way. If you're trying to calculate it, I guess you'll have to do that. There is a mistake here, though. That should be gone. Only the angular piece is included in the solid angle. I divided it away. That's what happened right there. So I typed that wrong when I typed it in there. Okay, solid angles. Everybody good with that? And so we have really two normalization conventions, two normalization conditions, one on a function we haven't figured out yet, but I'm going to talk about here in just a bit, and we'll finish up on Friday. And then the one that I've kind of beaten up a little bit, that's how you normalize the spherical harmonics, which are the product of the phi function and the solution that Legendre worked out for the theta function. That's how you normalize it. And so that's you're going to have to do one of those on the worksheet. I guess the bottom line is, don't forget the sine of theta when you do that normalization. It's there, it's in the volume element, but don't include the r squared and the dr, because that's reserved for the radial functions normalization condition. Okay, now that we talked about how to normalize it, okay, I'm not going to do it for every function. Griffiths has worked out, and you can see there's phi, right? That's phi. That's the theta function that we've been playing with here. All of this is that constant that has been normalized for you. We're not going to try to accomplish checking the normalization condition for any values of m and l. The tutorial has you do it for one particular function, m and l, and just verify that. People have tabulated these, though, and so if you look, this is the spherical harmonics, which is the product of those two things with the appropriate normalization conditions already worked out from this piece right here. Okay, wasn't it nice of people to tabulate that for us? And so you can see, remember, that was 1 before, I guess, but in order to be normalized over all space, by the way, just like there's 2 pi radians in a circle, if you go back to what I was talking about for these solid angles, all directions are 4 pi, and the units of those are steradians. And so it kind of doesn't surprise me that that turned out to be 1 over 4 pi square root as the normalization constant for what was 1, right? But it has to be that. If you take this integral and you integrate it over all directions, so theta would go from 0 to pi on theta, and phi goes from 0 to 2 pi. If you integrated over those limits, you would get 4 pi, okay? 0 to 2 pi right there, 2, and it just works out. So you can check that if you want, but that's where this 4 pi comes from. It's been done for all the other solutions as well. And here, I guess, is then the normalization condition, okay, for two functions y, indices with prime indices or unprimed indices. And that's, of course, a complex conjugate because this is part of psi star psi, okay, over correct the correct element, the two-dimensional element with the correct limits, because that makes all space, right? It's going to be a Dirac delta as long as L and L prime are the same and M prime are the same. You get 1 times 1. If L isn't L prime or M isn't M prime, it's two different states and they're orthogonal, and then you get 0, right? So this will either be 1 or 0, whether or not everything matches up or not. If they're different functions, you'll have Dirac delta turn out to be 0 there. So that's a statement of the normalization condition for the spherical harmonics, which are given in a table right here. It's a lookup. And by the way, for those of you that had me for modern physics, remember this was on your equation sheet in the blue boxes from Thornton and Rex's book. I know those of you that had Campbell used a different book, but I'm sure that they had normalized spherical harmonics plotted. I found this on the web at brilliant.com. It's a three-dimensional rendering of the normalized spherical harmonics. And if you've seen chemists, this is, since we're talking about the hydrogen atom here, this is kind of the way electrons seem to orient themselves around the nucleus spatially, at least with respect to angle. We're going to talk about where radially they find themselves here in just a bit. Okay, so that's the spherical harmonics, what they look like, what they mathematically look like, and of course our job is now to use them. And in order to do that, I guess I got to break out of this thing. So I'm going to stop share because I'm in a different PowerPoint now. We're going to talk about the radial function for the last couple of minutes here. Let's quit from there. Come on, quit. Yep. Nope. I don't want to. Do not keep the annotations. And I arbitrarily broke them up into 2 PowerPoints for no other reason than my own convenience of putting these things together. Let's now talk about radial solutions. Share that with you. Sure, I got the right one. That's that one. All right, yep, it's sharing. I see the green border. And so we'll go on and talk about the other piece. And just to remind you where we went from Schrodinger's equation in 1 dimension. Then we said Laplacian, Schrodinger's equation in multiple dimensions, in 2 or 3 dimensions, as you wish. We had separated out the spherical harmonics out that we just finished talking about from ours by going through this separation process. And we had completely ignored for the time being when we were talking about this on Monday and so far today, the radial equation. It's now time to deal with that. So I'll be working with this equation right here for now. And there is another tutorial that we'll pick up on Monday, be due on Monday, I guess, dealing with the radial equation. And remember what I said about the normalization convention for that guy. We'll be dealing with finding this. When you go to normalize it, don't forget the R squared, because it came out of the volume element, and we're going to need it. Okay, so here's the radial equation. And it turns out to be an awful lot of change of variables. Okay, and I you got to almost have a roadmap to keep track. Remember that, like, psi capital was equal to this psi of a position times e to the minus. Let's go with I e over h bar, which is really an omega, right? H bar times t, and then we took this guy, right? And we separated that guy up into a R piece, which we're now dealing with, and a Y piece. Okay, and then that Y piece, well, we beat that up and separated it out into a theta piece and a phi piece in spherical coordinates. And so now we're going to work at this. And we're not done yet. We're going to take this variable and we're going to redefine this thing u here, okay? Because I rewrote the angular equation that we left off with. with the appropriate separation constant we talked about, the L index from the Legendre polynomials and the associated Legendre functions, right? That same L, but it's positive in the radial equation when we separate it out. That was what was left, had all the radial pieces. And the first thing I did, I guess, is I brought the R, I multiplied everything by R. So that's gone, and I put it right here and here. Okay, so I just rearranged it a little bit there. And then just because we have to, I'm going to redefine a function, a substitution variable, very similar to if you're doing a calculus integration. I'm going to get rid of R, and I'm going to define it to be the product of R and R. And if you look at some of these things, you can kind of see why that might be a logical thing to do, okay? Because I got an R here multiplied by an R when I'm taking a derivative. It just will clean up the differential equation, transform it from being in terms of this R to this new variable U. And so let's work through that, okay? And so if that is my substitution variable, then if I'm trying to find R, it would just be U over R, which I like writing like that, because when I write it like that, I have a chance of getting its derivative correct. Okay, and you can see I need that dr with respect to R to go right there, okay? And so let's do it. I bring down the -1, I subtract 1, and it's a chain rule, right? Not chain rule, a product rule. So that was the first times the derivative of the second. And then I guess I got to go the derivative of the first times the second. And so I write it like that. That is the derivative of R with respect to R. And hopefully you can see the value of this when this shows up in the denominator, but I'm multiplying it by R squared. That means that term right there is just the numerator, R times du dr minus U. And so that kind of makes that guy a little easier. But then I got to take the derivative of that with respect to R. And so I think I did that correctly here. Let's see. So I had this derivative. So it's what did I do? I did, yeah, let's see. The derivative of where'd the two go? Where'd the two go? The derivative of, oh yeah, oh, there it is right here. So I'm taking the derivative of that, right, with respect to R. So it's R times the derivative of U with respect to R, the first times the derivative of the second, plus the second times the derivative of the first. Derivative of R with respect to R is just 1. And then I got to take the derivative of this thing. So I'm subtracting the derivative of U with respect to R. And neatly enough, those two cancel. That's what I get for this term. And that's, I think, the value of this. This guy right here gets completely replaced by that guy right there. And we just write the rest of the terms out. Okay? And so we're moving along here, trying to simplify the differential equation in R to something in U. Hopefully that will look a little simpler. And I think it will. And that's probably where, once I get there, I'll probably call it a day and we'll pick this up on Friday. Let's see. I substituted away R right here with what it is and here. Okay. And let's see. And then I think the next neat thing to do is to divide every term by R, which made that an R squared and made that an R squared. Okay. And let's see. Then the next thing I did was, and I don't know if it makes sense or not, but I multiplied by the reciprocal of that, h bar squared over 2m with the negative sign, okay, made this term positive and had no coefficients in front of it. And why'd I do that? Well, think about what Schrodinger's wave equation looks like. It has a minus h bar squared over 2m in front of a second derivative, doesn't it? And so this makes this thing look a little bit more like Schrodinger's wave equation. So that's the motivation for that. Let's see. Where did my R squared go right there? I'm going to go typo. R squared, right? It's there. It's there. Oh, nope, there it went. That guy which was left and that guy did cancel, not a typo. So we're good to go right here. And then so the last step, and just don't forget those two, almost did, bring that over to the other side of the equation since they're both being multiplied by U. Okay, and so that it may not look overly simplified here, But if you think about it, what I have with this substitution, as I said, the motivation for multiplying right here was to make that look like Schrodinger's wave equation. If all of this stuff, after I brought it over to the other side of the equation, because they were both multiplied by u, oh, and then I guess I did one other thing I didn't say. I brought the e to this side of the equation with the u. So that's why the e is back over here. If you do those kind of manipulations, and that's all it is, just manipulating, pushing symbols around the page, we'll call that thing right there V effective. And now it looks an awful lot like the eigenvalue problem we've been doing, which is H on psi is equal to the eigenvalue energy on psi, except the function here, the eigenfunction is not psi anymore. It's the thing that's related to the radial part of psi, but it's an eigenvalue problem. And the only thing we've had to do is we've had to accept that the potential isn't just a regular potential like for an electrostatic potential K Q1 Q2 over R. It is got an extra term on it, doesn't it? And if you've had the advanced mechanics class, I think everybody in here has taken that one from Kaiser. This is a centrifugal term. Okay, in addition to the potential energy that would be there, the KQ1, Q2 over R type of potential energy, there's another term analogous to the centripetal force. It's 1 over R squared, and that tends to push the particle outward, okay, at a greater radius. That's the effect of that term. It gives you a greater potential, doesn't it? Okay, so in any event, that's what we're going to be solving on Wednesday, on Friday when we come back. We'll be solving this equation with the full potential in. And guess what? In order to do that, we're going to be making another substitution. Okay, we're going to get rid of u in favor of another variable. We'll get rid of the r in favor of another variable u, and we'll keep working that for a particular potential on Friday. This guy right here. Okay, k q1 q2 over r with the negative sign. Why is there a negative sign? I guess because I've got one charge positive at the center, one charge negative, the electron, and so that's why when I multiply them together, the magnitude is e squared, but it's a negative sign. So that's the potential we'll be putting in, and we'll actually be solving this for the one atom we can do, the hydrogen atom. I look at my clock up there, and it looks to me to be right about 20 minutes after, so I have to let you go, I guess. By the way, I've drawn the potential here as well. We won't talk much about this piece right here. I'll just kind of ignore that. But you do realize it is impossible because of fermionic pressure, I guess. Fermi's law says those two guys can't co-occupy that space. So there is something right here. But we certainly are going to be using that potential right there when we solve Schrodinger's equation to get u ultimately, and we'll see how that goes. All right, don't forget the normalization. On this guy, it was r squared times dr. Well, if you remember, if u is equal to r times r, that does make your normalization of u a whole lot easier. You can forget the r in that case, and always going from r equals 0 to infinity. Anyway, I think that's it. Any questions before I let you go for the day? Stop sharing that. I will be scheduling office hours for 3 o'clock, like normal. If that's a bad time, I see a lot of the same faces at office hours over and over again, which is great. I love talking to those folks. I think it helps them out a lot. I do worry that other people aren't coming simply because I've scheduled a time when you're not available. And I'm more than willing to put it at any time during the day for you. By request, shoot me an email and say, hey, I got some questions. I'll find a time later on that day to set it up that works for both of us. That's all I got. We'll see you. Don't forget today's worksheet is the using Dirac notation. For Friday, we'll be doing the tutorial. It'll be due on these Legendre polynomials and associated Legendre functions. And then we'll be having hydrogen 1 for Monday and look at homework 7, 3 problems from chapter 3 that'll be due next week. And if you do find out anything more about Kaiser's midterm, shoot me an email or whatever telling me when's his exam. I don't need it from everybody. I guess once I got one, I'll give you a firm date on when we'll do the midterm next week. You guys have a great day. Hope everybody stays healthy, and we'll see you next time. Away they go. That's how I know you're listening to me. Everybody leaves on cue. Take care, folks.